It's my distinct pleasure and honor to be able to introduce the first speaker today, the President of the International Mathematical Union, academician Ludwig Dmitrievich Faddeev. Academician Faddeev is very well known for his work on the mutual applications of mathematics and physics to one another. Today, the title of his lecture is Functional Integrals over Orbits of Compact Groups.
Thank you very much, Professor Shenson. I think that all of us coming from Soviet Union yesterday, or Professor Gelfand is here for a longer time, are quite glad to be here and to be able to address this audience. And I would say that our joint interests are somehow the influence which modern mathematics now plays in modern theoretical physics, or vice versa. And so we'll try, all of us, I think, to convey you this message. For my own talk, I have taken this subject, functional integrals over orbits, which is not very new, I would say. It could be done many years ago, but maybe there was not enough motivation. The new, in fact, well, I'll tell about the story a little bit later. But the new motivation for such a subject came from the following observations. In modern theoretical physics, when we speak, I hope it's seen, well, next it will be a little bit better. When we speak about strings or conformal field theory, we encounter the entities, physical entities, which are called actions, which are usually functionals over orbits of some infinite dimensional group. So what is called Versumina-Novikov-Witten model is a model of field theory. So there is a field variable. This field variable is an element of the affine Lie group, and the function of these fields, which is called this action, I will not write it down explicitly, but anyhow, is, as it was realized recently, has a natural geometrical interpretation of as an action of symplectic form on the orbit of this affine group. The same for another famous example of conformal field theory, namely two-dimensional gravity of Polyakov. There also this action is functional over the, well, it's later. Well, I'm speaking about this part of my transparency. Excuse me. The same action is connected in the same way as with the Virasoro group, with the group of diffeomorphisms of a circle, or rather of its central extension. So having this in mind, it was quite natural to try to devise the calculational methods for this field theory. And as a first step, to go back to finite dimensional examples and experimentize with them. What can we do when we have examples of finite dimensional Lie groups, and what we can calculate by means of the beloved physical tool, which is called functional integral. The particular paper which I'm going to speak about was done in collaboration with my younger students, Anton Alexeyev, who is still undergraduate at university, and Shatashvili, who is young postgraduate at Siklov Institute. Now let me remind you what is functional integral in symplectic setting. I will do it first on the example of linear phase space. Of course, later we'll speak about nonlinear phase spaces. But in the case of linear phase space, when we have explicit canonical variables, P and Q, and which appear out of as a Darboux variables for the symplectic form omega, the dynamics of the classical problem is contained in the action functional, which is something like PdQ minus Hamiltonian times dt. And of course, quantum normalization is this factor 1 over h, which I'll drop later, which is called Planck constant. And the main entity in quantum mechanics is the evolution operator, so operator x to the minus I ht, where h is the Hamiltonian, is quantum mechanical operator corresponding to classical function h. And we usually write down quantum mechanics in terms of so-called, well, one or another representation, so coordinate representation. So we are to say what are coordinates and momenta when you are given symplectic form. So in more general terms, you are to say what kind of Lagrangian foliation you have on your phase space, if it's usually, if it's non-trivial. But anyhow, as soon as you have coordinates or Lagrangian coordinates, then the matrix element of the evolution operator between, it's a kernel in L2, let's say, is written down formally as an integral of the Feynman density, which has formal writing down as x to the I action times measure, which is formally something like Liouville measure over the phase space, written down as a product over all time points between initial and final time, so between time 0 and time t. So it's written down here as a product of these Liouville measures, normalized with 2 pi h volume of the cell in the phase space. And of course, this formal expression is to be understood as some limiting procedure, and one of these limits is explained here. You are to make finite dimensional approximation to the integral. So for instance, like you choose some time, you divide your time interval into n points of length delta t. You introduce coordinates pn and qn associated with each such a site in time interval. And you are to integrate a function which is finite dimensional approximation for action, for instance, of such form pi times qi minus 1. And for Hamiltonian, you are to take, for instance, Hamiltonian in points pi and qr, I, or other people prefer, and for good reason, coordinates, symmetrizing coordinates for each point here, so qi plus qi minus 1 over 2, or something else. Well, it's all formal things. We have to learn how to work with them when we're doing it. So rules of the game come with the game itself. But the important condition on the trajectories over which we integrate is that final and initial value of coordinates are fixed. So that final q is q double prime, this one, and initial q is q prime, this one. Whereas on p, we don't impose, on the momenta, we don't impose any conditions. The non-symmetry between coordinates and momenta, that's more subtle point, which will be important later, so I must mention it. It's a little bit uncomfortable, is that in fact we are integrating not over Liouville measure. There are one more momenta variables in this integration. There are n minus 1 coordinates and n momenta variables you are to integrate with. So there is some, to be more invariant, you are to think about this matrix element as a density. So you are to, the invariant thing is this matrix element times dq, the final dq, for instance, dq prime. And then, of course, this thing will be symmetrized. But one must remember these things from the beginning. So that's about functional integrals. I don't imply that by means of this device, one can quantize any quantum mechanical system. It's certainly not true that one can, using only symplectic terms like this, Liouville measure and Cartan action, to describe completely what is correspondence principle in physics. But we have, on the other hand, we have a lot of experience of doing these things, and in particular, in the case when we have additional symmetry, dynamical group, and especially in my case, I have it, we can use this device in a rather unique way. Some more comments about this thing. One must remember, for instance, that this functional integral which I described to you have a nice property that, of course, the evolution operator for time separation going to 0 must give you a unit operator. So the limit of this object when t, of course, not delta t, but this large t, it's a mistake, large t goes to 0 is nothing but delta function, which is, it means that all integration but 1 over p disappears, but one integration is still here, so you get this delta function out of this integral. That's all what I wanted to remind you about the functional integrals, and now let's turn to the problem of representations of compact groups. Professor Bott is here, so he has very refined method of doing it in terms of differential geometry. But I would somehow refer to the naive understanding of our orbit method, which I have learned from my colleague Alexander Kirillov. Namely, there is a well-spread attitude that the representations of the compact, of the all Lie groups, even infinite dimensional maybe, can be obtained from the correspondence principle when you begin with a classical system defined on the symplectic orbit of this group. So when I was learning it about 25 years ago, I have made an exercise. I also understand at that time that functional integrals are convenient tools. So I have made an exercise of finding out the representations for the rotation group by means of the functional integral. And first half of my presentation will be exposition of this exercise. Of course, this will be used somehow to get experience of doing it in more complicated cases, and maybe some of the comments will be quite, the exercise will be trivial, but nevertheless it will somehow give you some light on more general situation. So the group O3 orbits are spheres, two-dimensional spheres, let's say of radius m, and of course the volume of the orbit is 4 pi m. By the rules of quantum mechanics or by the rules of cohomology theory, it must be integer. And so it means that the radius which is allowed for quantization is integer or semi-integer. So I write some more formulas. Coordinates of the spheres are 3x subject to condition that sum of square is m squared. The symplectic form can be written in this way. And with respect to corresponding Poisson bracket, the coordinates xa are themselves generators, classical generators of the rotation group. Namely, their Poisson brackets is the one which it must be. Of course, this form written here is not in Darboux form. You are to say what are coordinates and momenta somehow associated with it. And as my phase space is nonlinear, and well, you understand that I cannot introduce global coordinates for which this form will assume the form dp dq. Nevertheless, by brute force, in this case it's easy, I can do it almost everywhere. Namely, I will introduce the spherical coordinates, and then in spherical coordinates, this form will acquire this form, modular normalization factor, d phi, d cos theta. So I can say that phi is coordinate and cos theta is momentum. But of course, this coordinate system is singular, and so I must pay for my brute force a little bit later, and we'll see in which manner it will be done. So let me tell you that second part of the talk will be associated exactly with this problem of finding Darboux variables of the orbits for in more general case. But in rotation, in the case of rotation group, it's quite explicit. You have seen that in the action functional, we use the integral of the symplectic form, so which we now use to write down as d minus 1 of omega. So one form omega can be out of this, in these coordinates, looks like cos theta times d phi, and you can add also some exact things, like, for instance, like gamma, constant gamma times d phi, because when you differentiate, this thing disappears. So that the action without Hamiltonian, we'll speak about Hamiltonian later, assumes the form radius times cos theta d phi, and this a constant which depends only on initial and final values of coordinate, gamma times integral of d phi. Now we remember that, well, I have written this naive picture that in fact I have brute force consisted in changing the sphere, which is a little bit clumsy drawn, by the product of the interval times circle. And of course, north and south poles are singular points for these things, and it is reflected by the fact that the action, when integrated over closed circle around this point or this point, is non-zero when the radius of this small thing goes to 0, which is not so good, but integral, the condition of, so in the Feynman functional, I don't need action. I need only x to the I action. So I have freedom of adding things modulo 2 pi, and exactly this condition is the same as quantization of the orbit. I see that 2 pi times, so m plus minus gamma, excuse me, must be integer. Of course, not 2 pi, but m plus minus gamma must be integer. So gamma is some auxiliary parameter. I can take it either 0 or 1/2 when m is integer or semi-integer, and this will fix me my action. So x to the I action now is well defined. So we can say that this is an example, the simplest possible example of the non-univalued action in sense of Novikov, which appears in this setting. Of course, Novikov treated mostly infinite-dimensional examples, which I referred to at the beginning, but here we have some rudimentary object of the same mathematical properties. Well, anyhow, this fixed me the action. And now, if I'm interested, for instance, in the matrix elements of the rotation around the z-axis, so the generator, the Hamiltonian for this rotation will be third coordinate, x3. I must write down this functional integral, so substituting q by phi's in the same way as I have done before. It must be a, not a. Well, so action now, change of the letters. I cannot write a for action for too long time. Action is usually s. So, so this is my action. Trajectory is phi of time and theta of time are subject to condition that initial value of phi is phi prime, final value of phi is phi double prime. But now we are to take into account this, I cannot say non-trivial topology, but trivial in the sense that easy, but still, but still non-trivial topology of the phase space. Phi variable. Well, I have a motto when I speak to students that in quantum mechanics, you always go to coverings. So what I have in mind is that you are to integrate over trajectories which are fixed modular full rotation around your z-axis. So this means that the full matrix element here is not the functional integral in the previous sense, but you also are to integrate over the fundamental group of the things when you deleted 2 points from the sphere. So you are to integrate the action with fixed values of phi prime and phi double prime with respect to the shifts of all these things. This observation, in fact, well, very natural, but this will be an important thing in getting us out of this paradox that I have especially pressed on the fact that functional integral for small time must give you unit operator. But what we are seeking now are finite dimensional representations. So we don't need operator, unit operator in the all L2 of phi variables. It's too large. We are to find out projection or finite dimensional kernel for this functional integral when t goes to 0. And essentially, this averaging will be instrumental in coming to these finite dimensional things. Of course, with respect to momenta variables, which is m times eta, we are still to integrate only over finite interval from -1 to +1. So that's the recipe. Let's say we'll find out that it leads us to the true result. But as I think that Feynman would not be against it, that one must somehow add rules as soon as you work, and the known example will give us assurance that these tricks are all right, and we can go to more difficult examples having this experience. So what is the formulation of the functional integral? You are to integrate your action, which is defined as soon as you have symplectic form, over you are deleting some points. In our case, these are stationary points with respect to rotation around the z-axis. You are to go to the covering, so you are to integrate over angles from minus to plus infinity. But about the adjoint variables, like eta in this case, you are still to stick to your classical interval. And at the end, you are to average over the this discrete group which defines your covering. Well, if you take this all into account, then the functional integral can be calculated explicitly very easily. Let me remind you that in the Darboux variables, like m, eta, and phi, my action is linear in phi variables. Hamiltonian doesn't contain phi. So all the, in this finite dimensional approximation, integrals of phi's can be calculated explicitly. They will give me delta functions. So n minus 1 delta functions will be lifted by n in minus 1 integration over eta variables, and I will remain with one eta integration. That's it. So my answer for this kernel G naught for fixed values of phi prime and phi double prime is given by one-dimensional integral over eta of the expression x to the eta times final phi minus initial phi minus time, because it was, and I remember also about this gamma term, which physicists call topological term for some reason, but it's a rudimentary example of theta term, excuse me, of this theta term which appears in more complicated examples of physical actions. I must remember about it also. So, of course, eta integration can be taken. I have written it explicitly in full details. And you are to do averaging. The role of this gamma, combining with m, shows that the nominator is periodic in phi variables. If m is integer, this term is absent and it's periodic. When m is semi-integer, this must be added, and once more you have periodic things. So the only non-periodic expression is denominator, so you are to evaluate such sums. At this point, I must confess that 25 years ago, I thought that this sum is cotangents. So And because of this, I was making a lot of adjustments for integer orbit or semi-integer orbit and so on. And I had in mind, well, I had psychologically also pressure of Kirillov results about characters when he integrated not over the classical orbit, but over some shifted orbit. And so I thought that it must somehow appear here also. Now I changed my mind. I said that this sum is not cotangent, because it will be cotangent when you make this sum in a way as a principal value summation. And I will substitute it. As I say, I'm doing experiment. I know the answer. I must get it. I will understand this sum for one term and second term in different way. So I will add, let's say, some regularizing multiplier like this. And then, of course, I will get sine over alpha over 2 downstairs. It must be. But then I will get additional exponent at the denominator. So the average of these two terms would give me cotangents. But I'm taking it like, you know, like upper limit from upper half plane and lower half plane rather than the principal value. With these adjustments, with this recipe for understanding the averaging, I will get my final answer, which gives me sine of m plus 1/2 of phi prime, phi double prime minus phi prime minus t over sine 1/2. You can divide them, and you'll get the sum over, in fact, taking into account gamma, sum over some integer exponents of em phi with integer m after adjustment. And there will be 2m plus 1 such exponents, as it must be. You are getting 2m plus 1 dimensional representation of rotation group as soon as you quantize the orbit of radius m. In particular, for infinitesimal time, you are getting this projector. And we certainly understand that we got projector instead of unit operator because of this averaging. Now let me explain you why this recipe is natural in the some alternative way. If I averaged first under the integral and then consider integral, you remember that phi variable come into this integral. Let me show you it once more. Phi comes in linearly, so you get expressions like x to the em eta times 2 pi and sum over them. So you have to use Poisson summation. And you will acquire, for the one-dimensional eta integration, density which contains delta functions. And you are to say, so some of them, some zeros of this delta function will come into interval from -1 to +1. And you are to say, and you are to look if the zero of delta function come onto the end point of the interval from -1 to +1. In fact, it comes into places, and you are to understand this integral over eta with this delta function as extension of interval from going down a little bit from -1 and going up from +1 to take all this delta function into account. So this means that delta function for the zero on the point of integration must be taken with the coefficient 1, not with 1/2, but with full coefficient 1. And then you'll get the true answer. So so geometrically, you have deleted 2 points. You got a cylinder. You went to the strip. And you are to enlarge the strip a little bit. Then it will give you the true answer. So that's the trick. How to get the finite dimensional representation of rotation group out of this essentially infinite dimensional object like functional integral. Of course, well, this example is known to many experts. On the other hand, until now, you can find it, I will make some physical remark. Until now, you can find in the physical literature the statement that the classical model for spin is a top. This is nonsense. Classical model for spin is a sphere as a phase space and not as a coordinate space. And this is exactly the explanation why it is so, because quantizing of the spin is finite dimensional representations of rotation group, and it's here. So that's, with some small corrections, is my exercise of 25 years ago when I studied myself the orbit method. And now, with motivation which I told you at the beginning, namely that we are to go to infinite dimensional groups, we decided to make, with my collaborators, intermediate step between rotation group and infinite dimensional things, namely consider, well, series of classical groups. And it's clear from what I have told you that the main thing to calculate this functional integral in this way is to find the Darboux variables, so the analogs of these phi and eta variables for all other orbits. And in the second part of my talk, I want to explain you how to do it. One way of doing it for the case of the unitary groups. Of course, we can do it also easily for orthogonal groups. For symplectic, one must still work a little bit more. It was, I cannot claim that it's maybe what I will explain to you is the most natural way to do it, but at least it's connected with my experience with working with the constrained Hamiltonian systems. And so I will derive you the true Darboux variables on the way of solving constraints which define the orbit as embedded in some higher dimensional phase space. So let me tell you a little bit how it can be done. So the orbit is a factor over maximum torus, but I will, so you can write it more explicitly. I have freedom of doing, instead of co-adjoint orbits, adjoint orbits here, but in more, I must remember that it's not so all the time, but in this case I can do it. So my orbit in the terms of group variables is given by this expression. This is a point M, and of course everything which commutes with M naught is factored out here. So in the unitary case, M must be anti-Hermitian matrix with zero trace if I'm treating S special case. And now how the Kirillov form looks on this orbit. I claim that it can be described, there are many ways of doing it. In my particular coordinates, it can be described in the following way. One must consider the two form, M is this point, times the GG minus 1 squared and trace. Of course, it's understood in the terms of matrix valued differential forms, so this is not zero, in spite that I consider square of the same form. And then I must understand that this form, in fact, is constant over the leaves of the compact group, and so I reduce it by symmetry on the orbit. But on the other way, one can say that this is a lift of the symplectic form on the whole group, if you want to do it so. And so in a way, it defines you also in some other variables, in some bigger phase space, rather trivial symplectic form. And the one on the orbits must be obtained from it by means of the Hamiltonian reduction with respect to constraints which defines the orbit. So more explicitly, let me write it down more explicitly, the original form, and then constraints with respect to which I want to reduce it. If I consider the eigenvectors of matrix M. Its eigenvalues are written in the, well, with this normalization for some reason, 2i times, they are pure imaginary, 2i plus some real numbers m's. I order them in particular way, and of course, sum of them is equal to 0. Then, and also, if I introduce complex variables like rotations of the given basis by means of the group, unitary matrix, then in these variables A's, I have two n squared real variables, or n squared complex variables. I get a form which is exact, and so it's, so d minus 1 of it can be written in the simple way, this imaginary factor times these real numbers, and then ak dak, where ak, as I told you, are n complex vectors. So in the phase space of 2n squared, of dimension, of real dimension 2n squared, this is linear symplectic form. One can write down corresponding Poisson brackets and so on and so forth. To go to the orbit, we are to remember that we have that G was unitary matrix. This was orthogonal, orthonormal basis. So in fact, my variables satisfy some quadratic constraints that their scalar product is different from Kronecker symbol by 0. So these are constraints on my variables. Constraints are divided naturally into diagonal part, phi I, and non-diagonal part. In the enlarged phase space of all independent A variables, the diagonal part is scale time, is generator of some scale transformation, and they commute with each other. Moreover, they do commute with any variable which can be considered as a variable on the orbit. So any variable which is invariant with respect to this maximal torus actions. So physicists call such constraints first class. On the other hand, non-diagonal, so they commute with each other with respect to this enlarged Poisson bracket and commute with any function on the orbit. On the other hand, non-diagonal part of constraints, you can calculate their Poisson bracket explicitly. Essential here that it's proportional to the difference of eigenvalues of matrix M. Their Poisson bracket is non-degenerate. Those are called second class. This means that the physical space phase, or the orbit, which must be obtained by imposing these constraints in the enlarged phase space, is obtained in the following way. If I consider the submanifold defined by constraints, it will not be symplectic manifold, because the first class constraints are still, their orbits are in the dimension, in direction of the null vectors of corresponding to form. So they, as I say when I lecture to physicists, first class constraints are killed twice. They kill themselves, and they're also adjoint variables with respect to them. So that if it's taken into, I think that this geometry is known to everybody. So for a check, let me calculate the dimension of the true physical phase space, or that of orbit. 2n squared was my original dimension. Then I had n constraints of first class. They kill twice, so I multiply by 2. And then I had n squared minus 1 over 2, and this complex dimension, so to make it real, this factor. So in the way I get the dimension n squared minus n, so dimension of the group minus dimension of the Cartan subgroup, which is dimension of the orbit, of course. So in this language, this number is obtained by discriminating between first class constraints and second class constraints. Of course, I'm treating the non-degenerate orbit, which corresponds to the case that the highest weights, the eigenvalues of this matrix M, are different. As soon as some of them coincide, I get singularity in this Poisson bracket. So some second-class constraints turn into first-class, and you are to do reduction a little bit higher. You will get lower dimensional orbit. All counting here acts automatically, and so you will get these orbits immediately. But I will stick to the case of non-degenerate orbit. So all these M's are different. Now, what do we do when we are writing functional integral having constraints, when you have some first-class constraints? You are to find out the analog of Liouville measure, as you remember from my beginning. And the trick which I advertised in also about 20 years ago was as follows, that you are to introduce auxiliary conditions which are essentially conjugate to the constraints of the first class. So you're essentially to make all constraints, so the combination of constraints and auxiliary conditions, as we call them, are to give you system of functions not in involution, not singular system of having non-singular system of Poisson brackets, and then make corresponding reduction. The choice of auxiliary conditions is in your disposal. So here art begins. You are to choose something which will lead to the most tractable form of the functional integral. And so, in a way, the first contribution to this subject was understanding, well, proposal of such auxiliary conditions in this particular case. So my collaborators told me, why don't we try the imaginary part of the last coordinate? So what is here? I is vector index of the, is a number of the variable A, which was vector variable. N is the last component of this vector. And so I require that imaginary part of this last component is 0. It turns out now with this you can calculate now new extended system of Poisson brackets, and it will be non-singular, and so that's a nice auxiliary condition. Of course, once more, one must still have somehow put in some subconscious that if the last component was 0, so on lower dimensional submanifold, this is bad subsidiary condition, and so in a way, reduction, well, it must reflect itself in the reduction somewhere. But I am doing generic, I'm speaking about generic situation and doing trying to find out these Darboux variables on the main part of the orbit. Other things will appear by themselves in this procedure. So I don't want to bother you with the calculation. Still, some of them I will present you a little bit. It's all straightforward now. The most interesting thing is outcome. So let me lead to it in several steps. As soon as you have imposed this condition on the imaginary part, the explicit form of the one form alpha, which was an imaginary part of something, shows you that the real part of this last component also disappears from the form. So in fact, you have here form of the form, excuse me, m times a variables a's projected orthogonally with respect to the last element of my basis. So perpendicular is this symbol here. These vectors now are not orthogonal, so this is the orthogonality condition. And of course, these are last components of these vectors. And because the original system of vectors was orthonormal, the sum of this, now sum over I, over the numbers of my vectors is equal to 1. And they are real on my submanifold because I required that complex, imaginary part of them was equal to 0. So in spite that I'm dealing with complex numbers, here the geometry a little bit later is purely real. I can write down these AIs as some isometric in real sense matrix C times B. This matrix mapping n minus 1 into Cn, but in real sense, independently for real and complex parts of my, imaginary parts of my variables, satisfies this condition. C star is 1 minus projector, and projector is real. So in fact, I can use the matrix elements of these things as real. It's important because then it turns out that when one calculate this form in new variables, you will get once more the form, the quadratic form of the matrix M, which is the reduction of original matrix into this n minus 1 dimensional space with this, the same things, BP times differential VP minus complex conjugate. Now it's a nice problem in linear algebra to say that, of course now, as you understand, the important part here is that differentials of C disappeared in this calculation because of reality of them, they do disappear. So only differentials of B remain, not differentials of C. But now, it's not quadratic now. It's not quadratic now in my variables because now the matrix elements of this matrix are now depending on my variables B. You remember that they somehow, these are now variables. The beautiful result of the linear algebra, I want now to, once more, to go to the diagonal part of it. And the beautiful thing of linear algebra is the following, that we have found, well, one can prove it from variational principle, but in Gantmacher book about matrices you can find this exercise, is that the eigenvalues of this new matrix, which is n minus 1 dimensional, as soon as my variables go through their own domains, runs once between these adjacent eigenvalues of original matrix M. So new variables M with subscript 1 lies between these two adjacent matrix eigenvalues. So turning to this diagonal form of M, I find that now my form alpha looks as follows. These variables MP with subscript 1 times C dC, where C is once more orthonormal system. But now M's are variables which are somehow having values in these subintervals. You remember in orthogonal case, it will be the end of my reduction because M at that case was minus 1 plus 1, and so that's and M subscript 1 is my eta variable lying between 1 and minus 1. Here we are still to go further. It's not of Darboux form because M is variable here, and C, it's cubic in variables if you want, if I can say so. But now I want to repeat my trick. Now I have no possibility of introducing auxiliary condition, but I can change variables. And I will change variables in such a way that I will extract the angle of the last component of my C vectors, n minus dimensional vectors, by introducing phase in them, and require that new ones, which are now, I return to my notation A, P goes from 1 to n minus 1 with subscript 1, that their imaginary part of the last component of it is equal to 0. Extracting this angle will give me the expression of the form, that all these M variables will be multiplied by differentials of these angles. So I have this first sum. And then in the remainder, I will get essentially the original expression where I have non-constrained vectors. Well, excuse me, opposite. Vectors which are constrained, that their imaginary part of last component equal to 0 times these things. So first and second term. This is essentially inductional thing. I have reduced my n-dimensional case to n-1 dimensional. I can repeat it several times. In this way, I'm getting, this of course is of Darboux form because it's m times d phi. And this is not, but I can do it once more, and so on and so forth. In this way, some hierarchy of variables will appear. So I will get variables m with a subscript k of the level k, and number of them is equal to n minus k. So for fixed k, the number of i's goes from 1 to n minus k. And they lie in this pattern that the variable of the next level lies between two variables of the previous level. All of them are continuous. And there are also, this is half of variables, and conjugate variables to them are angles phi, which varies from 0 to 2 pi. So in this, the main part of the orbit for which these variables are kind of good is written as a product of this polyedro of these variables and torus of dimension n squared minus n over 2. I want to say now that many of you have also realized that these are, so in this way, I have got variables which can be considered as a classical analog of Gelfand-Tsetlin basis. Because in the Gelfand-Tsetlin basis, you have integers which numerate you the basic elements, which somehow are arranged in the same picture. Let me draw this picture. So originally I was given these parameters, m1, m2, and so on, ordered in some way, which defined me orbit. These were eigenvalues of this matrix n, which define me orbit. After quantization, orbit must be integer valued. They are, as in first example, either integer or semi-integer. Now, but in classical case, they are just arbitrary variables. And now the Darboux variables for this orbit are arranged in this table. Each variable in the interval between two of them lies between two of them below here. And the main part of the orbit looks as written in Darboux variables. One can do the same thing for the orthogonal case. In that case, of course, this reduction goes from even dimensional orthogonal groups to odd dimensional orthogonal groups a little bit different. So the construction of these Gelfand-Tsetlin variables is a little bit more complicated, but can be done through quite explicitly. So at this point, when we realized it, I consulted Professor Gelfand. What did he know it? Well, maybe. My understanding of the story is as follows, that he certainly, in a classical book of Gelfand and Naimark about the classical groups, the Plancherel formula was written explicitly in terms of these variables. Plancherel formula over the group. So this for that case, of course, the upper level was also to be used as variables. So these are, after quantization, highest weights, and so on and so forth. So the product of these variables themselves and the meaning of their full product, of the Liouville measure, if I can say so, was clear. But the canonical interpretation of that apparently was not. So that's my understanding. But as soon as you have now this picture of variables, then you write down functional integral essentially in the same way as I have done for my previous example. You have to remember about this enlargement of the orbit a little bit, that this body, this polyedro, inside of this polyedro of p n squared minus n over 2 must be a little bit enlarged. And then essentially all integer or semi-integer points which are lying in this table are the labels of the basic vectors, as it is in Gelfand setting construction of the representations of the group. So functional integrals here also serves its purpose. It, without too much pressure, gives you the result which you wanted to obtain. This allows to speculate that going to infinite dimensional examples, this experience can be used to make explicit quantization of these famous conformal invariant field theoretical models. The work on this is in progress. I have some preliminary results with me made by these co-authors, Alexeyev and Shotashvili, but it's not finished yet. A side remark about this, maybe as follows. Of course, in the original A variables, the functional integral which I calculated could be considered as a cubic interaction integral, because I had a, free variables, essentially, this coming from linear symplectic form A's, and then quadratic constraints on them. In the functional integral language, quadratic constraints can be put into action by corresponding Lagrangian multipliers, so you will have some cubic terms in your action. So in linear variables, the integral which I have calculated have cubic terms in it. It's not Gaussian. And so the quasi-classical approximation for it is not true. On the other hand, by going to more complicated variables, I reduced it even to linear integrals and calculated it explicitly. So I think that we are still to analyze which kind of cubic actions can be treated by this change of variables. For me, in particular, this is very important because I did not mention at the beginning one more motivation for this work. In treatment of so-called anomalous field theories, which began with my paper on so-called Schwinger terms in the Gauss law commutation relation. So when you treat four-dimensional Young-Mills theory interacting with so-called chiral fermions, the naive functional integral does not work. My approach, which was based on some naive homological algebra, was to say that after quantization, some constraints which were classically first class turn into second class. So there is enlargement of number of physical variables in this system. So there is additional, which can be taken into account by adding some particular term into action. This term, it also has orbit-like interpretation. So the fact that the integrals associated with the orbit can be calculated explicitly makes me a little bit optimistic that I can calculate this contribution of this particular term into functional integral explicitly also. And I need to calculate it explicitly to be listened by physicists because it's a term which is not 1 over h order, but 0 in h order. So it must be in the quasi-classical or loop expansions, it must be evaluated explicitly. So I hope that maybe, well, I will make a conjecture that this particular action, which has an interpretation of one cocycle of the loop group in the four-dimensional case, in the case when the base manifold is four-dimensional, can be calculated explicitly, but work on this must be done. So I began with some propaganda for infinite-dimensional case, really cheated you and treated only finite-dimensional case, but returning back to infinite-dimensional motivation. Well, it's quite usual in modern mathematical physics. I hope that at this point I will finish. Thank you for your listening.